Previously, we've seen how looking at how the electric potential in some region varies can give us the electric field. Now we're going to spend a bit of time seeing how doing this qualitatively can help us to do things like draw better electric field line diagrams. So as a working example here, I'm going to go ahead and revisit our friend, the electric dipole. Now, in an earlier video, we had worked out that we could intuit the equipotential surfaces that were close to the charges, because we know that close to the charges, they had to be spheres, because so at that scale, you're sufficiently far enough away from the other charge that doesn't really count. And we also worked out that the plane that bisects the two charges was an equipotential surface, because since the electric potential followed superposition, we could say the potential at any point was equal to K times Q over the distance from the positive charge. And then since the other charge was negative, this would be plus K times negative Q over the distance from the negative charge. So anywhere where R plus and R minus, the distance from the positive and the negative charge is the same, that would correspond to where the voltage was 0. And so that would be anywhere on this plane right here. We then kind of reasoned out, we could think about what some of the other contours would have to look like, kind of reasoning that you have to kind of morph from these spheres over to this plane shape back over to spheres here. And so we reasoned that, say at some intermediate location, the equipotential surface would have to look like this. And if I can draw something reasonably symmetric, well, I tried something like that. So while we can follow the rules that we followed before for drawing electric field lines, and we certainly will, we can now also take advantage of the fact that electric field lines have to run from high potential. So this is some large positive number here, to low potential. So this is some negative number over there. Let me just remove those just to declutter the drawing again. And all the way along, the electric field line has to be perpendicular to the equipotential surface. So this is in exact analogy, if you're familiar with skiing, to following what's called the fall line, which is the direction of whatever steepest descent is in the area. Basically, if you're to drop a rock right there, where would it start skidding down the mountain? So this allows us to finally be able to cleanly draw things like horizontal electric field lines, because we can be guided by the fact that these are perpendicular. And so this way we still don't need to remember all the elaborate rules that I alluded to, because we can just imagine if we do need these perfectly horizontal lines, we can just use the fact that you have to go from higher potential to lower potential, always crossing the equipotential surface perpendicular. So those lines would look something like that. And we could draw in some other lines. Let's just do 8. So we've already done 4 there. There'll be another, whoops, I don't want those stubs to be quite that long. Do kind of 4 there. And then here, 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 here. So here I'm just leaving, heading out radially and crossing perpendicular. But now when I go from the one to the other, I have to follow a path that will be everywhere perpendicular to the surface. So not the best art, but there, I'll just draw in a little perpendicular so we know. And you just do the same thing everywhere else. This one is going to go off screen, loop around, and eventually come back in. Whoops, over here somewhere. Probably better if I just follow that one off like that. So somewhere up in where I've written words, this would loop over. And we can do the same thing down here. Maybe. Yeah, something like that. And this is actually when you have a computer drawing electric field lines for you. This is actually how the computer really does it numerically. Is it goes ahead and the usual programs compute the voltage everywhere and then calculate the derivatives in the area to figure out where the fall line is and follow the fall line. But if you're a good artist and you're drawing this in 3D, this is an exact to-scale solution for the electric field strength of the dipole everywhere. Another application of this that I do want to get into is revisiting conductors in equilibrium. So if you remember here, if we had a conductor that was in electrostatic equilibrium, so I'm just going to make it look, I don't think I want it that big. We'll make it a little smaller. So say I have a conductor, I need to make it really pointy at the one end. There we go. If I have a conductor in electrostatic equilibrium like this, things we've already worked out were that the excess charge had to be on the surface. And if we're in equilibrium, the electric field strength everywhere is equal to 0. So just as a very quick pause and ponder here, ask yourself, what does that mean about the electric potential inside the conductor? Pause and I'll get back with you. Okay, so what it means is that the voltage is a constant. It could be any number, positive, negative, or 0. The main thing is that we only have an electric field if the value is changing. So say this entire conductor here could be at 1000 volts. And if I look at any two regions, well, it's 1000 volts. There was no change in the potential. And if there's no change in the potential, there's no electric field. So we already saw that. We also saw that the electric field is perpendicular to the surface, right at where it comes off or goes into the surface. And again, this was arguing that if it wasn't, charges would shift around because of the sideways components of the electric field that would exert sideways forces on the charges along the surface until they redistributed so that the electric field lines were perpendicular. And this is a process that usually takes less than a billionth of a second. So this leaves us with the one thing that I'd been promising but hadn't had a chance really to show yet. And this is that the surface charge likes to pile up at pointy spots. And so we can now start to reason why that is. Since we know that the electric field has to leave perpendicular to the surface everywhere, I'm just going to draw little electric field lines going out. say like this. I'm trying not to make them very long, and I'm certainly not going to draw all of these later. And since we're leaving perpendicular, that means that in the immediate vicinity of the conductor, the equipotential surface will basically just look like a form-fit surface around the conductor, like so. Now Ask yourself, though, if you get very far away from the conductor, and so far would mean substantially farther away than whatever the longest dimension of the conductor is, what would the conductor look like when you're that far away to you, and what would the equipotential surface look like out there? Okay, so out there, it would have to look spherical when you get far away. The reason for this is that if you're far enough away, this conductor will look like a point charge. So now this gives us the clue for why the charges have to pile up here at the pointy spots. This is because as I have to morph from, say, this triangular shape to a sphere. As you do this, the pointy bits have to do the most work to unfold. So this might be the next one, and then the next one, like so, and I'm not going to draw the rest. But the point is that in this region right here, the equipotential contours are closely spaced. And that's because you're having to change from a very tight radius to a much smoother radius to start to mesh in with the rest of the equipotential contour on your way to becoming a sphere. Well, if the contours are closely spaced, this means that the electric field in the region is strong. So the electric field lines will be spaced relatively close together in this region versus, say, out here where the spacing is broader. But if I have a stronger electric field, we know that near the surface of near any surface, the electric field strength near that surface has to be proportional to the electric field strength. So therefore, the surface charge density is high. So this is why when you look at photos of lightning rods, or you just look at a lightning rod, like for instance where I live, I'm not too far away from a golf course, and because golf courses have large, open surfaces, and you have people carrying metal sticks around, it's usually a good idea to put some lightning rods up in unobtrusive places around the course. There happens to be one that I can see pretty readily from the road, and when you look at it, you can see up at the top are these really this really sharp pointy spike. And the whole point of that is that since charge likes to pile up at pointy spots, and the electric field will naturally be stronger there, lightning bolts will be more likely to want to jump to that pointy spot way up than, say, to some golfer's 5-iron or something like that. Alrighty, so in the next video, we'll go ahead and start taking a look at capacitors, although we will start by making a brief detour on Kirchhoff's loop law. See you over there.